Wow.
It's all right. I see how it is.
So last time we talked about MO diagrams, we looked at simple homonuclear, meaning two that are the same atoms. Today we're going to look at some heteronuclear, where they are different atoms, and we're going to hopefully learn something that way. Are there any questions about homonuclear stuff right now? Big thing is when we drew those p orbitals and pi orbitals, you understood what was going on there in terms of the overlap. We have not talked about S and P mixing. S and P mixing, if you look at like N2, what happens is some of the orbitals shift, and that's because of symmetry overlap. I really don't want to talk about that right now. Okay, let's keep moving on to other examples. NO. No. This is an interesting molecule. How many electrons or valence electrons does this system have? 11.
Yay.
It has
7. Yes, exactly. What type of system is this? The good kind? Actually, a not good kind. Well, actually, it can be pretty good. Depends on if you're at a Fish concert or not. I don't know. Yeah. No, actually, they flood this on babies, newborn babies. Poisonous gas. What it does is it messes with the binding curves of the hemoglobin. It makes it bind oxygen way tighter. There was a graduate of the chemistry program who's now the chair of biochemistry at Berkeley who determined that. The way he found it out, he was studying cuttlefish, and he thought cuttlefish were really cool. And they have these types of detections for their bioluminescence. It led him down a really weird path. And if you've ever seen incubators where they have babies like who are suffering, they flood this gas over them. Anyways, it's radical, dude. NO dot. I'll just represent it that way. What do you know about radicals? Unhappy, reactive, generally paramagnetic. Okay. We're going to draw the MO diagram for this one. Okay. Really depends on your preference. Whoa, bless you. I'm going to put nitrogen on this side. I'm going to put oxygen on this side. NO in the center. It really is just preference. Some people like to have the more electronegative element on this side. Some like it the other way. I'm just going with this. Okay, we need the electron configurations for nitrogen and oxygen since we got two different systems. In this case, nitrogen, ramble off the full electron configuration. Oxygen. I like the race to the finish. It's fun. Okay. So we really only care about the valence shell. Here's the valence shell. Yeah, the core sometimes are involved, especially at high pressure or other weird conditions, but we're just going to neglect them for now. Okay. We have to draw the atomic orbitals. Now, these atomic orbitals, they're the same symmetry, the same type of orbitals, right? Okay, I'm going to draw nitrogens like this. Give yourself a little space here, okay? 1s, oh, not a 1s, 2s, 2p. Okay, we can fill electrons here. I'm going to use orange because I have it in my hand. That was way too loud. Okay. Bless you. Loud sneezer. Okay. Oxygen. Oxygen's also going to have a single 1s and, single 2s and 3 2p's. But there's going to be a shift in the energy. Why is there going to be a shift in the energy? Different sizes, yeah. Different ionization energy. Putting more electrons in, yeah. I want to get more, all of that stuff's related to one thing. I mean, electronegativity is related to all of them, but I want even more basic than electronegativity. Yeah, nuclear charge. Which one has a greater nuclear charge? Okay, which one has a smaller radius? Oxygen also has a smaller radius. The nuclear charge is bigger. The electrons are delocalized. They get sucked in, right? Okay, the electrons are being pulled in closer. What would you say about the relative energies of these orbitals? Are they going to be higher in energy, or are they going to be lower in energy, given there's a higher nuclear charge? 50-50 shot? It's going to be lower in energy. Nope. As you go from left to right, the radius gets smaller. What happens as you go down the periodic table? It gets bigger. Why does it get bigger? Yeah. Pauli exclusion principle, you have to start filling electrons. Do they all really want to be really close to the nucleus? Yeah, they do. They would love it because it's energetically favorable, but they repel one another. Mm-hmm. Yeah, so what were you saying?
Yeah, no, I remembered that it does actually
get massive. Yeah, there is weird relativistic effects that happen here that can cause different changes, but I don't want to talk about that. Okay. Yeah.
Could it be summarized as also the shielding? Like
yeah.
Shielding effective nuclear charge?
Yeah, it's all about, it's all based upon shielding. It just becomes like shielding's a difficult thing to talk about in some cases. The other thing is you use Slater rules, which are like, which means you'd have to fall back to quantum mechanical calculations, and that just seems like a boogeyman. like really? Okay. Fill in electrons. 1, 2, 3, 4, 5. What am I going to do with that last one? Yeah. Okay. Now, the energy previously, when we've looked at homonuclear atoms, or molecules, the energy levels have been the same. We know the symmetry is there. We just pair up similar orbitals, right? What's going to happen in this case? Yeah, they have to be within a certain energy of one another to overlap. Even if they're really far away in energy, they still slightly overlap, but when we think back to like those coefficients of mixing, there's some contribution there mathematically. A lot of times in this qualitative form of MO theory, we just say it's not contributing. But there would be some factors there. Okay, so what's going to happen between these two s orbitals? Yep, we're going to get a bonding and anti-bonding state. Okay, I should have drawn this one higher, but I didn't give myself enough space. Also, this thing is not centered again. Damn it. Okay, what type of overlap is this? This guy? Yep. Okay. Now, before we keep going, if I were to look at the contribution of nitrogen and oxygen to this new bonding MO, they're not equal like they once were because we had a completely covalent system. Now we have a situation where there's a difference in electronegativity. And we have a difference in the contribution based upon energy and overlap. Looking at this sigma orbital, is there more contribution from the nitrogen or from the oxygen? It's the oxygen. It's closer in energy. It should have been shifted a little bit more to illustrate that. What about the anti-bonding orbital? Which one is there more character of? The nitrogen. Yep. I am super happy you guys sound bored while saying that. That means, or you're just all exhausted from the semester? I don't know. Well, sorry. Never mind. I thought you were like, this is boring, old hat. Or you just think it's boring now. I don't know. But it sounds like you have a good understanding of what's going on. Okay. That's important to understand. What about this stuff here? What's going to happen there? Same thing's going to happen. They're going to overlap, but tell me what's the result. What should I draw? I should draw a line here. Yep. Yep. Okay. Now I'm going to draw dashes to show. Okay. This sigma, if I were to draw an MO for it, where would there be more contribution? On the oxygen. What about the pi's? Also oxygen. So if I were to draw those pi orbitals, this is exaggerated. But they would look something like that, right? Because there's more contribution from the oxygen. Sorry, this is the nitrogen, that's the oxygen.
That's because more electrons or because it's closer in energy?
Closer in energy, and if you look at that linear combination of atomic orbitals, you'll find a higher coefficient on the oxygen side. Okay? Looks like a gangster talking out of one side of their mouth. My grandfather used to talk that way. I kind of talk that way. What about the pi star? What way would that look like? So that would be one of the pi's. Pi star. Yep, there would be bigger contributions here. Smaller on this side. Let's do it that way. Okay, how many electrons do I have in total? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. What would I want to target? What atom would I want to target if I wanted to break this thing apart? Yeah, I'd go with the nitrogen. There's more contribution on that side. Try and find a way to react it that way. Or try and pull that thing off. Okay. Any questions about that one?
Do you see NO positive commonly in nature, or is that more?
So do you see NO positive in nature? I don't really know the answer to that one.
Or is it more stable just for it to be radical and deal with it?
The only thing I really know about it is it adopts two conformations, one a bent and one a linear when it's a ligand or behaves as a ligand. So in iron, when you're talking about hemoglobin, it does this like sort of bent orientation. And honestly, right now I can't remember if it does it through the oxygen or through the nitrogen, but I believe it's through the nitrogen. I can't remember. I'll check back into that and get back to you, Aiden.
Wait, so because if you're bonding to nitrogen, would you be adding
You would be, and that's going to increase that bond length. There's different things you can do to make it happen. Or shoot, or not happen. Any other questions about this one? Yes. A hammer can open a door in many different ways. It depends on what approach you want to take. Yep, does that? And it's an unsatisfying Yeah, it made sense. Yeah, a lot of times people would donate into a pi star to rupture a bond. But you could do other things too. You could try to pull electrons away from here, make things drop. There's other mechanisms to make things happen. Okay? Sorry, any other questions about this one? Okay. Let's look at HF next. This, yeah. Okay, how many electrons in this system, valence electrons? Yeah. HF is really weird. We're talking about gaseous HF. We're not talking about aqueous or liquid because that becomes way more complicated and it's very strange. It has extremely strong hydrogen bonds. I will introduce them to you as gases, but in inorganic, you will most likely talk about them in aqueous solutions. And you can make red shifts or blue shifts happen, and there's a rationalization behind that. Okay? Yeah, inorganic was my favorite chemistry class. Actually, organometallics was my favorite chemistry class in undergrad. You can always calculate it. Okay. Electron configuration. Hydrogen. Fluorine. What do we got? Yep. Yep. Okay. We're only going to really care about these these valence. What about hydrogen? Yeah, it only really has the valence. So we're going to consider those ones. Okay. 1s1 in relation to these other valence orbitals is much higher in energy. So there's our 1s1. Fluorine, here's our 2s. Actually, I want it lower. Yep. We've experimentally determined it, like through forms of spectroscopy. The other thing is we can calculate it too, and it really has to deal with, this has so many more protons, it's getting pulled in. Also, the electrons in this system are less effectively shielded because there's more electrons that keep on getting tossed around. Okay, and then 2p. We used orange last time. Let's keep with orange. What'd you say? Jeez, bless you. They're not the same energy level. The 2p is lower. Okay, tell me what's going to happen. Yeah, the 1s and the 2p are going to interact. The 2s, there is some symmetry combination that actually lowers the energy a little bit. So this one gets lowered some. There's sort of a contribution here. It gets lowered a bit. That one we're going to say is relatively non-bonding, so we're going to put an N here. People might debate me on that. They're within their right. I would go with whatever the coefficients say from the quantum chemical calculation. That's why I kind of don't like labels in some cases. In some situations, it's very clear-cut. Other situations, it's not. Okay, Lily, what else did you say happens? Yep. There can be some overlap between the 1s and the 2p. How many p orbitals are going to overlap with that 1s? Yep. So this is our hydrogen. Hydrogen only has that, right? So let's call this. Sure. We could have overlap that way. Why not py or pz?
That would be
like it's lined up with the middle.
Yep. So here, there wouldn't be quality overlap. If we get these two, like the orange and the white, to overlap, is there net any interaction that happens? No. They're out of, there's no net change there. Okay, so it's only one of these orbitals that interacts with the s. So what type of overlap is this between the two white orbitals? Yep, so we get a sigma, and then we have to have a higher energy sigma star. Now, what about the other two p's? Yeah, non-bonding.
Is this supposed to be slightly higher?
No, I wanted to draw them close to each other in energy. I don't know that without doing the calculation. Okay, let's fill in some electrons. 1, 2, 3, 4, 6, 7, 8. That sigma orbital, where's there more character on? Yep, the fluorine. Probably should have drawn that a little more drastic than I did here. What about these things? If I were to look at the highest occupied molecular orbital, HOMO, these non-bonding, what are they? Yeah, they're lone pairs, basically. Oop, there's that guy on the fluorine, and then the other one that's coming out of the board. There's just no contribution from the s orbital. So they're just kind of a p orbital sitting out in space. Yep.
That's probably a bad way of me wording it, but more of it didn't work out.
In this area of chemistry, no matter what way you word it, you're going to make somebody mad. I went to an entire conference. The conference I went into Amsterdam was just a bunch of people arguing about what they said is. Do bond via what? Yeah, in some cases. Yep. There's situations where they do, like xenon, krypton, even argon. You can make reactive or at least make stable things. Okay. Any questions about this one?
Are we just gonna do this qualitatively?
You are gonna.
Have like a sheet with the.
Mhm.
It's got like the list with the different energies.
Yeah, we're not going to do that. We're just going to do it qualitatively. We are going to calculate stuff with density functional theory and then apply it. And we're going to use some of the ideas we're seeing here. So to answer your question, yes and no. We're going to draw stuff like this. We might talk about some numbers, but the numbers are going to come from quantum mechanics. Okay? Am I cool to erase this? Okay, another benefit of this MO theory is we can talk about bond strength. We have a measure of it. You guys remember bond order? Measure of the strength of a bond. Okay. We're just going to shorten it to BO. You remember how to calculate it? Mhm. Yep. Okay. Let's calculate the bond order for each of these because we've had made those molecular orbital diagrams for these things. So you're going to have to go back and check and look. Of course, I did it out of order. I couldn't do it in the order I listed them. It's got to be me. Okay. H2. Let's look back.
1.
How the value will be 1.
Okay.
No, it's okay. How many electrons in bonding orbitals?
2.
Minus.
0.
Yep, gets us to a value of 1. What does that 1 mean, or what could we relate it to?
Single bond.
Yeah. If you're using the ideas of Lewis structures and you're really tied to them, they're related to one another that way. Okay, oxygen. Let's calculate that one out. Minus 4. Total of how much? 2. What does that mean? Double bond. When we draw the Lewis structure of oxygen, draw it like that as a double bond. I ask students in general chemistry, why is this so reactive if it has a double bond? Why is this so reactive even though it has a double bond? It is a diradical. We draw it this way. Lewis structures suck. They're just a way to help us represent things. There's situations where you can break them. A lot of situations where you can break them. Okay. HF. Minus. Total how much? Yep, single bond, NO. What?
Another feeling of Lewis structures.
Yes. Resonance, it's there. You see a fraction of a bond order? Most likely resonance is to blame. Remember, resonance is nothing more than just the failure of a Lewis structure. The idea that bonds alternate is not true. We represent it that way sometimes, but it's not correct. I know Dr. Ogawa has strong feelings about that one, which I agree with. There are some organic chemists that will draw it out that way and say, yeah, but we all know what's going on. And that's okay too, if we all understand what's going on. But bonds like this, like they're not flipping.
Does he prefer the dotted line?
Yeah.
Yeah.
The dotted line is the better way to go. I like to do it because I'm a lazy P chemist. I go, whoop, like that. Then they go, how's that thing going to react? And I go, I don't know. Leave me alone with my computer.